Welcome to EE361 PreLab Guides. This is Professor Hiren Krada, and in this video, we are going to look at PreLab number 8, or as we like to call it, the Big Enchilada. This is a very fun lab. It's actually really fun to build, and well, actually fun depends on your perspective, of course. For EE engineers, it's a lot of fun to build and even more fun to operate when you get it working. Well, let's take a look what the lab is about. In this lab, let's see, we are going to use a technique known as pulse width modulation to control the speed of a DC motor. So here is the lab. And the title of the lab is Digital Pulse Width Modulator Controlled DC Motor. Okay. Oh. So digital pulse width modulator control DC motor. So let's take a look first at what pulse width modulation means. Okay, pulse width modulation. Now, pulse width modulation is a technique where we actually take a series of digital pulses and we change or we vary the width of those rectangular pulses. So a rectangular pulse in digital circuits looks like this. And okay. All right. So a pulse is going to look like this. It's a rectangular pulse, right? This is one full cycle. So this is one cycle. And each of these are half cycles, right? Or we say positive half cycle or negative half cycle. But in case of this rectangular digital pulse, we term this as on and this as off. So if you look at this cycle, this one cycle is divided into two parts, on and off. On could be for a digital signal, let's say typically 5 volts to 0 volts. In the lab, in lab 8, I think this level is set to 10 volts. So the on level is set to plus 10 volts and off level would be 0 volts. Okay, so now out of one cycle, we have some portion of the time. Again, remember, x-axis is always time. So some portion of the time of that one single cycle, we have a high voltage going in. The other rest of the cycle is 0 volts. So the ratio of on to off, or actually the percentage of time where the signal is on, is referred to as the duty cycle of that rectangular pulse. So this is the digital signal, digital rectangular pulse signal. And the percentage of time that it is on is termed as the duty cycle. So obviously, if it is on for 100% of the cycle, meaning if your cycle is here and here, and we say it's going to be on for 100% of the cycle, well, the next cycle is here. So guess what? 100% duty cycle is basically DC, right? It's a DC. So 100% duty cycle would be a DC voltage. If we set the cycle to 10% or 10% on, we get a very thin rectangular pulse. The rest of the time it's off. And then again, it's on for 10% of the cycle, and then it's off. So this is a, well, approximately 10% duty cycle. Now, in this 10% duty cycle, what is the average value? If this was plus 5 volts and this is 0 volts, the average value, or VRMS would be what? 10% of Vmax, which is 10% of 5 volts. Okay. So similarly, a 50% duty cycle simply means that the cycle is on for 50% of the time. Sorry, the rectangular pulse is on for 50% of the time, and then it's off for 50%. So on, off. This is one full cycle. This is half the cycle. And so you get a 50% duty cycle. Actually, let me not use DC because I'm using DC over there. So duty cycle. Okay, 50% duty cycle. So 50% duty cycle, the average value of this waveform would be 50% of max. And this actually answers question number 2. So let's take a look at the PreLab questions. All right. So PreLab number 2, given that 50% duty cycle is being applied to the transistor, so what is the average voltage that the motor sees? Well, that is the information that we just covered. You find what the Vmax value, and then you average it out, and 50% of Vmax would be what the motor sees. Okay, so that's question number 2. Now, coming back to our rectangular pulse. This is known as the width of that pulse, okay, width of the pulse. And notice what we are doing. When we change the duty cycle, we are changing the pulse width. So duty cycle change is basically pulse width modulation. And pulse width modulation. Okay. And so if you change the duty cycle, we are changing the average value being applied at the output. Since the average value is changing, the current and voltage being supplied to the DC motor changes, and hence the speed changes. The higher the voltage, the faster the rotation, or faster the speed of rotation. And so the larger the duty cycle, or the higher the percentage of the duty cycle, the faster the motor rotates. The lower the duty cycle, the slower it's going to rotate. So the speed is directly proportional to the duty cycle. Okay. So duty cycle, actually the other way around. The speed of the motor is directly proportional to the duty cycle. Okay, percentage of the cycle. And so that is what we're going to do in this lab. We are going to set up a circuit that is actually going to vary the duty cycle that is being applied at the output of the circuit, and that output of the circuit is fed as the input to the DC motor. So let's look at the circuit first. Now, the circuit might look, well, it looks complicated, but let's break it down. Okay, let's break it down. Let's see. What do we have here first? We have the motor at the far end, right? We have the motor at the far end. And the motor, of course, is made up of an inductive coil, can be represented schematically as an inductor. So it requires a large amount of current to flow through. And hence that motor is driven by this transistor, 2N2222 which can actually supply that large amount of current to that motor. Now, what we're going to operate the transistor in is basically we are going to operate it in a cutoff or saturation mode. Okay, cutoff or saturation. That is the output of this chip right there. Okay, VO. This is VO, and VO comes from pin number 7 of this chip, and it goes into the base of that transistor. Okay, so we are working our way backwards from the output towards the input. Okay, so the DC motor is connected to the transistor. The transistor is connected to the output of this chip. Let's look at what this chip does. This chip is 74LS85. 74LS85. It is a 4-bit magnitude comparator. Okay, it's a 4-bit magnitude comparator, and as the name suggests, it compares 2 digital bits together. Okay, so that is the comparator. So 74LS85, that is the comparator that we are using for this lab. So this comparator, as the name suggests, will compare 2 quantities together. Now, this is a 4-bit magnitude comparator. So it compares the magnitude of the incoming digital signal. Okay, so let's take a look at the pin configuration. The pin configuration here, it's a 16-bit IC, it's a 16-bit chip. So let's zoom into this right now. And all right. Okay. So 2 of the pins, of course, are for power supply. So pin number 16 and 8 are where plus VCC and ground are connected. And then, as you can see here, we have inputs A and B, and both of them are 4 bits, right? 4-bit comparator. So they go from A3 to A0, A0 being the least significant bit, and then you have B3 and B0. And it compares both these numbers together. And so that's why we have 1, 2, 3, 4. And then B3, B2, B1, B0. So those are the 8 pins for these 4-bit numbers. Then we have 6 outputs. 6 outputs right here. And depending on what we want to do or what the circuit designer wants to do, they can use any one of these outputs. Okay. So what we are going to do is we are going to apply digital signals to B3 to B0. And then there's a counter connected to A3 to A0. So we have 2 numbers, and we are going to look at pin number 7. So we are going to look at output A less than B. Now, what do these outputs mean? Okay, so we have outputs connected from pin numbers 2 to pin number 7. Okay, and what it's going to do is it's a condition. So it's a condition. For instance, when A equals B, meaning when the input A, digital input A is equal to digital input B, output 3 and output 6 is going to go high. Okay, it's going to go high. So the outputs go high, or output is true, when the condition is fulfilled right there. And so for our circuit, for our design, we are using pin number 7, which is A less than B, meaning for all inputs or all values of A which are less than B, the output 7 is going to go high. Okay, the output 7 is going to go high. And so that is basically what we're going to do in our circuit. You're going to use this 4-bit comparator. You're going to have 4 bits or 4 digital signals going in. We compare A with B, and for every number where A is less than B, pin number 7 is going to go high. Okay, so let's look at the circuit diagram again. So here is A and here is B. Okay, that's what they're doing. Now, the other outputs are we are not using, so they're connected to ground, and pin number 3 is connected to plus 5 volts. Right now, we won't worry about those. Okay. So let's talk about the B input. Okay, B input. Again, it's a 4-bit number, so it goes from B3 to B0, right? B3 to B0. So B3 to B0, of course, can take 16 values, going all the way from 0, 0, 0, 0 to 1, 1, 1, 1. This is 0, this is 15. Or in hexadecimal, this is 0 and this is F, right? What we are doing is, well, we're taking the output pins B3 to B, sorry, not output pins, the input pins B3 to B0, and we connect them to ground. Okay, so if you look at this pin configuration right here, these are all connected to ground. Now, of course, we have a resistor in there to limit the current and also to prevent a short circuit between our plus 5 volts and ground. But essentially, these pins B0 through B3 are all connected to ground right there. Okay, and ground, of course, is 0 volts. So the de facto state for B3 to B0 is 0. Okay, then if you see the same connections and you follow these connections, they are connected here to something known as a dip switch. It's a dual inline package or dual inline pins. Basically, it's 4 switches in one. You can mount it directly on the breadboard. And each of these switches is connected to plus 5 volts. Okay. When the switch is in the lower position, switch is in the lower position, it's off. And when you move it up, the switch becomes on. So when the switch becomes on like this, it has a connection and a path to plus 5 volts. So now your pin number B0 is connected to plus 5 volts, right? B0 is connected to plus 5 volts. Now, to save us the trouble of disconnecting this line, because if this resistor was not there, if this 330 ohm resistor was not there, then you'd have plus 5 volts connected directly to ground, meaning you'd have a short circuit in your power supply and you would end up blowing it out. Okay, so hence the resistor in there. So this is how we would set pin numbers B0 through B3 to zeros and ones. Okay, if the switch is off, then the digital pins B3 to B0 are 0. And if the switch is on, then it gets connected to plus 5 volts and you have a 1 input going in there. Now, at the same time, what we are doing is we are connecting. So it's the same. Let's continue with B0, right? B0. When the switch is on, you have plus 5 volts right here. And B0 is connected to plus 5 volts. So digital 1 is going in. And at the same time, that plus 5 volts is connected to the anode of this LED. Now, the anode of the LED is connected to 1, and the cathode is permanently connected to ground. So if the switch is open, let's just look at the LED. If the switch is open, then the anode of the LED is also connected to ground, meaning the LED will remain off. Okay, LED will remain off. But when you apply a digital 1 to pin number B0, then plus 5 volts is connected to the anode of the LED, and the LED would turn on. And so that is an indicator that digital 1 is being applied. Okay, so hence the LED should display a 1 when the switch is on, which will indicate that digital 1 is being sent into the input. Okay, that is the purpose of the LED. So it seems as if it's a complicated circuit, but when you actually lay it on the breadboard and we look at the configuration, everything has a purpose, and it doesn't feel that overwhelming. So let's see. So that's basically the B input. Okay, we can control what input the digital number B is going to have depending on the state of the switches. We can set any number between 0 and F, okay, between 0 and F, okay. So now let's take a look at digital input A. The digital input A again is the same. It's A3 to A0, okay, A3 to A0. And the inputs to that digital number is coming from this chip. So the output of this chip Q3 to Q0 is directly mated or directly connected to digital pins A3 to A0 of our comparator. So B, of course, is going to be set, right? We're going to set B to a particular fixed value, and then it is going to compare the incoming signal of A to B. And whenever A is less than B, pin number 7 is going to go high. If A is equal to or greater than B, then output would be 0. Okay, so this is going to be critical when we try to draw a timing diagram. Okay, so let's take a look at what this chip is. So this chip is 74LS163, and it is a free running counter, and it is something that you have used before. It basically counts in binary form for every clock pulse. It's a 4-bit counter, meaning it goes from 0000 to 1111, 0 to 15, or hexadecimal F. Okay, QA or Q0 is the least significant bit, and QD is the most significant, meaning from left to right. Okay, now if you look at the counter, it is a positive edge triggered. It's a positive edge triggered. Let's see. If I look, let me see. The clock is right here, and yeah, it seems it should be a positive edge triggered. Anyway, so when the clock signal arrives, the counter will start counting, and the output will increment by 1 digit in binary. So if the incoming clock signal is 0, then the outputs are all 0. When the clock goes high, the output's going to start flipping or start counting, going through 0000 all the way through 1111. And depending, of course, on the frequency, you can control the speed of this count. All right, so let's see. Positive to negative transition and clear input. Okay. So we are going to take a 1 kilohertz and 5 volts peak-to-peak signal from the function generator, rectangular pulse, and connect it to the clock input. Now, there does not seem to be a bubble on there, so it is a positive triggered clock. So every time the clock goes high, the counter is activated and the output will change. Okay. So again, remember, if there is a bubble means it is negative triggered. Absence of a bubble means positive triggered. And this sideways line caret symbol, meaning it is edge triggered, meaning when it goes from 0 to high at the positive transition edge is when the counter is going to count. That is very important to keep in mind when you actually draw the timing diagram. Okay, so the operation of this counter chip is rather straightforward. You connect the clear signal to plus 5 volts, meaning in the absence of any plus 5 volt signal, of course, the output will be cleared. We do not want that, and so we connect this clear signal always to plus 5 volts. Okay, we have no need to reset the counter. As soon as we apply the positive pulse coming from the function generator, the counter is going to start counting. Okay, now when we say we are applying a 1 kilohertz signal, where it's 1000 cycles in 1 second. So it's going by very fast. Don't even, you'd have to be able to see the signal on the oscilloscope. Okay. So the counter timing diagram is going to go from 0001 and so on and so forth, right? Every digit will keep flipping. So this is Q, this is going to be Q3, this is going to be Q0. I believe in the spec sheet is QD and QA. Okay. Anyway, so this is 0, 1, 2, 3, and so on and so forth, all the way up to 15. And that output of the counter is our input as digital signal A, or digital number A, into our comparator. Okay. So now let's take a look at the question. The question is, that we have a free running counter, right? And it's being fed into the comparator. It's being fed into the comparator. And the output of the comparator is set to detect A less than B, right? A less than B. So the output of the comparator will go high whenever A is less than B. The condition is that we want to generate a 50% duty cycle, a 50% duty cycle. Okay. So let's break it down. In order to generate a 50% duty cycle, so A less than B would give us VO as plus 5 volts or logic 1 or logic high, right? And what we want is, we want a 50% duty cycle. 50% duty cycle for VO, meaning whatever output we have, whatever we count as one cycle for VO, we want VO to be on for half the time, and we want it to be off half the time. Okay, so it's on and off and on and off. So at the beginning, I think each, and we want this to be 50%. Now think about what this means. A less than B should result in 1, right? And we want a 50% duty cycle, meaning for half the time when the input's coming in and it's comparing A to B, for half the time, A has to be less than B. Okay, A has to be less than B, not equal to, not greater. It has to be less than B for half the time. So if you look at the number of states, this is a 4-bit counter, right? 4-bit counter. So what are the number of states possible? 16 states possible, right? And so on and so forth, all the way until we get 1, 1, 1, 1. So this is 0, 1, 2, and so on and so forth till we get to 15. Or in hexadecimal, this would be F. Okay. This would be VO, and we can call this Q3, Q2, Q1, Q0. Well, actually, not Q. This is for both A and B. Okay, A and B. So actually, let's look at the question. The question asks timing diagram for what? Oh, so it's asking for VO versus Q0 and Q3. Okay. All right. So let's go back to our, so it's right earlier. Q3, Q2, Q1, Q0. Now, Q3, Q2, Q1, Q0 is being fed as the input to A. So this also represents A, right? This also represents A. This is hex. This is actually just this decimal state. And VO would be separate. VO would be separate depending on what we set B to. So if we set B3, B0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on and so forth. Again, B also has the same number of states, right? It's a 4-bit comparator. And now we have VO. And what do we want? What do we want? We want VO to go high when A is less than B, right? Now this is going to be A. This is A3 to A0, right? A3, because output Q3 to Q0 is being fed as input to A3 to A0. So if A is less than B, then VO should go high. Otherwise, it should stay at 0. So we set B3 to B0 to a value where the incoming A3 to A0 will be less than B for half the time and greater than B for the other half. Okay. And that would only be possible if you set the value of B in the middle. You have 16 states, right? 16 states. So what does it mean? You have to set the value of B at 1, 0, 0, 0, which is 8. Okay, 1, 0, 0, 0. 9, sorry, 9. So if you cycle through the 15 states, if you cycle through the 16 states, VO will be high for 8 states, for the 1 for 8 states, and VO will be 0 for the other 8 states. So it'll be the halfway point in the count, okay? So for instance, set B as a digital number to 8, which actually not 8. We need it to be 9 because it has to be less than 9. And so it'd be 1, 0, 0, 0. And well, that's actually your answer. You set it to 1, 0, 0, 0. So every time the counter counts and goes from 0 to 15, it'll go 0, 1, 2, 3, 4, 5, 6, 7, right? 0, 1, 2, 3, 4, 5, 6, 7. This is decimal 9 and digital 8. So I think I'm confusing you students. Hold on. So decimal 9 and digital 8, and in binary, it would be 1, 1, 1, 1. Well, I mean, sorry, 1, 0, 0, 0. Okay, so the counter is going through its states, right? 0, 1, 2, 3, 4, 5, 6, 7. Well, 0 through 7 would give you 1, 1, 1, 1. Now, when it is 1, 1, 1, 1, it is still less than 1, 0, 0, 0, right? 1, 0, 0, 0. 8 states, 0 to 7, 8 states, and it is less than 1, 0, 0, 0. So if it is less than 1, 0, 0, 0, well, then VO is going to go high. So for all values A less than B, VO is going to go high. And then once the counter goes to 1, 0, 0, 0, 1, 0, 0, 0, then at that point, A will equal B. And if A equals B, then V out will go to 0. And then A is greater than B for the rest of the time. So V out will stay at 0. Okay. So again, For 0 to 7, meaning for 8 states, A will be less than B. And for the other 8 states, A will be equal to or greater than B. And so you have a 50% duty cycle. And this table is what you will use to create your timing diagram. So your timing diagram should look like this. Let's scroll down. Now, obviously, I'm not going to draw out everything for you, but I'm going to show you that if this is the clock pulse, let's draw a reference y-axis. You start a clock like this. It's a 1 kilohertz clock. It doesn't have to be to scale, but you should be consistent within what you're using. Okay. And then this is your clock. This is Q0, Q1, Q2, and Q3. Remember, Q0 through Q3 is also A0 to A3. Well, it triggers on the positive edge, right? Positive edge. So what happens? First positive edge, it starts counting. Q0 goes high. Q0 goes high. 0, 0, 0, 1. So the first, it is all 0, 0, 0, 0. For the first edge, Q0 goes 1. And then for the next positive edge, which is right there, it becomes 0, right? So it is 0, 0, 0, 0. Now it becomes 0, 0, 0, 1. And then so on and so forth. 0, 0, 1, 0. And then this goes high. And this remains 0. Fourth clock pulse, it goes to 0, 0, 1, 1. This goes 1. This stays 1. Okay. So this is A3 to A0. Now, your B3 to B0 is completely fixed, right? B3 to B0. And so now I've shown you the cycles for like 4 clock pulses. So every time it goes into positive transition, it's going to change its state. So this time it goes to positive. It's going to stay at 0, 0, 1, 1. And then when it actually goes through 16 cycles, you're going to have the full timing diagram going from 0 to 15. Now, as I said, B3 to B0 is going to be fixed. You'll fix it at the value that I just talked about earlier. And so it doesn't actually need a timing diagram. It's not changing, right? It's fixed at a particular position based on the position of the switches. And it simply compares these with, these outputs with B3 to B0. And then V out will go high. So I'm just drawing V out going high. And because we are using A less than B, whenever A is less than B, it's going to stay high. And then sometime in the future, when A is equal to or greater than B, it goes to 0. And so that's what your V out is going to be. Okay, that's what your V out is going to be. So by changing the width of the pulse that is coming out, basically V out, we can change the speed of rotation of the DC motor. And the way we change the width of the pulse is by using a counter and comparing the numbers with a preset determined number. So once you're done with this, I would highly recommend that you think about what other kinds of duty cycles you can generate using the set values for B3 to B0, right? B3 to B0. So you can change, again, let's go here. And obviously here where I showed, you can change the value of B3 or B digital input B by changing or flipping the switches. So the switch positions will determine what value B has. So if B is set to 1111, well, guess what would happen? For all instances, A is going to be less than B, except when A goes to 1111. So for 15 out of 8 out of 16 cycles, A will be less than B. So you would have the highest percentage of the duty cycle, 15 out of 16. That ratio would give you the percentage of on and off. And the lowest would be when B is all equal to 0. If B is all equal to 0, then, well, think about what would happen. A would never be less than B. Okay, what would happen in that case? And I will leave you with that question to ponder over. Hope this guide is helpful. This is well, I would like to say it's a very beautiful circuit, especially when built correctly. It's a lot of fun to do. You might encounter some frustration while trying to build it, but again, take it step by step. I believe the lab itself has a outline of the breadboard and an image. And so you can follow this outline and you can see by using minimum number of wires and cables, you should be able to build out your entire circuit. Okay. Take it step by step, just connect. I would recommend starting from the end, meaning connect the motor first, then connect the transistors, then make the connections of the comparator, then the counter, and then of course the LEDs and the resistors. That's where most of the work is going to be. But of course, your instructor might have some other tips and suggestions. So always follow what your instructor tells you in the lab. And of course, reach out to any one of us if you have any questions. Okay. So my email is hstrada@calpoly.edu. Let me know if you have any questions, and good luck with the pre-lab as well as the lab.